Hi guys, in this lecture we are going to introduce the concept of a limiting reactant and determine how to calculate the limiting reactant along with a number of other very useful concepts related to the quantitative analysis of chemical reactions. So as usual, whenever possible, I like to start us off with an example that we're all very familiar with. So the concept of a limiting reactant can actually be explored in the context of making cheese sandwiches. So if you follow the recipe for making a cheese sandwich, you take 2 pieces of bread and 1 slice of cheese, put them together, and you get your cheese sandwich. So let's suppose we have a situation where we're given 28 slices of bread and 11 slices of cheese. All right. In this scenario, we can start making our cheese sandwiches, but what's going to happen is as soon as we use up all 11 slices of cheese making our 11 sandwiches, we're not going to be able to make any more sandwiches, and we are going to have a total of 6 slices of bread left over. Okay, now whether it's hot dogs, hamburgers, sandwiches, whatever it might be, we all have some direct experience with this, right? We've got multiple ingredients. We inevitably run out of one of those, and that ingredient that we run out of is going to limit the number of sandwiches that we can make at the end of the day. And so in this case, we would call the cheese, in this case, will be what we call our limiting reactant. Okay. And the bread, in this case, we have extra of. So we could say we have excess bread. And in theory, right, the number of sandwiches that we can make is going to total 11. So we have a theoretical yield of sandwiches of 11. Okay, so I introduced a couple terms there that you perhaps haven't used in the context of making cheese sandwiches, but these terms are going to be very useful in our analysis of chemical reaction equations. So let's define each one of these guys in turn. All right, we'll delay there. All right, so the limiting reactant in any sort of chemical reaction equation is going to be that reactant that is available in the smallest quantity, the smallest stoichiometric quantity. So that would be like the cheese in our previous example. And this limiting reactant will be completely consumed during the course of the reaction, and it's going to limit the amount of product that can be made. All other reactants, right, so where there could be more than one, any other reactants that do not limit the amount of product that can be made are called excess. So this would be the bread in our previous example. And then finally, the amount of product that can be made by completely using up that limiting reactant will be our theoretical yield. So in our previous example, our theoretical yield of sandwiches would have been 11. So to sum all that up, we see cheese is limiting, bread would be excess, and we have a theoretical yield of sandwiches of 11. Okay, so now what we want to do is to take this concept and map it onto a general chemical reaction equation and basically say for any given chemical reaction equation, we want to be able to determine limiting, excess, and the theoretical yield. So a method for doing this is basically going to build upon what we've been talking about previously with our grams to grams, mole to mole conversions. Okay. And so the approach we're going to take is to take the initial grams of starting material, convert those into moles. Use mole to mole conversion then to convert the amount of each reactant into product, right? So let's say you have 2 reactants, so convert all of reactant A into product and all of reactant B into product. And then you're going to identify the reactant that makes the least amount of product. The reactant that makes the least amount of product will be limiting, and the amount of product that that limiting reactant can make will be our theoretical yield. Okay, so as always, I think working through an example is essential in this case. Now I'm going to point you, however, to if you are having a hard time with these concepts of mole-to-mole conversions, gram-to-gram conversions, and you need a little bit more background in terms of building up this concept of theoretical yield, I do have a little playlist posted on YouTube consisting of 4 videos that will essentially build up this concept starting way back at the beginning of counting individual atoms. So anybody who's having a hard time with understanding the concept of theoretical yield, I encourage you guys to maybe watch these videos, and it'll make sense some of the more challenging problems that we're working through here. All right. So that said, let's go ahead and jump into our first example. In this case, it's oxidation of magnesium here, and basically we are taking a reaction mixture that's comprised of 42.5 grams of magnesium and 33.8 grams of oxygen, and figuring out which one of these two reactants is the limiting reactant and what's going to be the theoretical yield for this reaction. All right, so our first step, as I said, is to convert our grams of starting material into moles. So when we do it for both the magnesium and the oxygen, using the molar mass of each to get the moles of oxygen, then use a mole-to-mole conversion factor built on this balanced chemical reaction equation that was given to us to determine the number of moles of product that each one of these reactants could hypothetically form. Then you're going to only pick the smallest number, the smallest of these two values, carry it down here, and then do your final grams to mole to gram conversion factor using the molar mass to get your final answer. Okay, so let's plug in some numbers and see where we land. If we start off with our given quantity of magnesium, divide by the molar mass of magnesium and oxygen, use our conversion factor from the balanced chemical reaction equation, we find that it is in fact magnesium that gives us the least amount of product. And as a result, the limiting reactant is going to be magnesium. Once we have that molar quantity of product that is formed from the limiting reactant, we can then multiply by the molar mass of that product to get our final prediction, which is the theoretical yield as to how much magnesium oxide we can form if we use up all of our limiting reactant. Okay, so let's work through one more example here. Let's suppose we're given a new reaction now, where we have NO and H2 coming together, and we're given a fixed quantity of both of those reactants, and we want to figure out how much ammonia we can form in grams. So we're going to proceed in the exact same way. We're going to carry out a grams to mole conversion using the molar mass for each one of these given starting reactants. We're then going to use a mole to mole conversion built upon that balanced chemical reaction equation, looking at those stoichiometric coefficients. Determine how many moles of product we can form, take the smallest, multiply by the molar mass, and we'll be home free. So plugging in the numbers, we have 86 and 25. We're going to divide by the molar masses. We are then going to multiply by those ratios, that mole-to-mole conversion factor, where we are constructing conversion factors based on those stoichiometric coefficients. Then we determine that it is in fact NO that makes the smallest amount of ammonia product, and therefore our limiting reactant is going to be NO, multiplying by the mass, right? Multiplying the amount in moles of ammonia that we could form by fully reacting that NO by that mass gives us the grams of NH3 that we predict could form in theory, which is of course our theoretical yield. Now, as one little bit more involved problem, it essentially requires the same exact techniques, but just a little bit more work. is given here in this reaction involving titanium oxide and carbon. So in this reaction, we are given values of reactants in units of kilograms, right? And we're wanting to figure out which one of these two compounds, titanium dioxide and carbon, is going to be limiting. So proceeding just as before, we've got to convert our initial masses into moles, but we're not given grams right off the bat, so we actually have to carry out a kilograms to grams conversion, then divide by our molar mass to get moles, then carry out that mole to mole conversion problem, take the smallest and plug it in. So if we do that for this example, we'll go through it quick. Feel free to pause the video as needed, right? Basically, we're taking those kilogram quantities, carrying out the math, and what we will find is in fact that the least amount of product in this case is the titanium dioxide, right? And so titanium dioxide is going to be our limiting reactant, and so then we will take the number of moles of titanium solid that will be formed in this reaction if we completely use up that limiting reactant, convert that into grams using the molar mass, and then into kilograms to get our final answer, okay, which is 52.9 kilograms of titanium. Okay, so that sums it up for our discussion of determining the limiting reactant, the theoretical yield, and the excess reactant. Now, in the final part of this video, I want to introduce one more concept, which is related to the fact that when we're actually carrying out chemical reaction equations, we're never going to get 100% of that limiting reactant forming our desired product. Things are going to happen, okay? And so this brings us to a discussion of the concept known as percent yield.